This video is the beginning of chapter 6, where we start talking about random variables. So the first type of random variable that we're going to talk about is discrete, and then sort of towards the end of this first section of chapter 6, we'll talk about continuous random variables. Now, we've seen continuous random variables in the past without really identifying them as such when we dealt with normal curves. Okay, so a random variable is just going to be a variable, but the value of that variable is going to be determined by some random process. So that's why we refer to them as random variables. All right, here in this section, we're going to talk about the probabilities. We're going to be able to compute the probabilities of certain events using a probability distribution. That would be the probability distribution like table for the most part, especially when we're talking about discrete random variables. We saw these in the previous chapter, and that was a table that listed all the probabilities, all the outcomes that are possible for a particular situation, and then their corresponding probabilities. All right, we'll talk about how to calculate and interpret the mean or the expected value for a discrete random variable. And we'll also talk about how to do the standard deviation for that as well. Our calculators will do that for the most part. It's a pretty tedious process, so we'll rely on our calculators for doing those calculations for the standard deviation. And then at the end of this section, we'll start talking about the continuous random variables as well. All right, so the probability model, and we talked about in the last chapter, this model is going to describe all the possible outcomes and then all the probabilities, the likelihood that each outcome is possible or the probability. So let's look at an example. Tossing a fair coin 3 times, and let's define a random variable x. So we use capital letters to sort of define the random variable, and then we'll see that we're going to be using lowercase x to represent the individual values that x can take on. So we're going to define x, random variable x, as the number of heads we get when we toss this coin 3 times. So if you think a little bit, you could see that we might get no heads, which means we got 3 tails. We might get 1 head, and there are 3 ways in which we could get 1 head. The first toss could be a head, the other's tails. The second could be a heads and the other's tail, or the third could be a heads and all the other's tails. So there's 3 possible outcomes that would result in 1 heads and 2 tails. And then likewise, there's 3 ways that we could get 2 heads and 1 tail, or in other words, 3 ways that we could get 1 tail and 2 heads. So you can see the list there. It's pretty obvious. And then there's only 1 way where we could get 3 heads, heads, and heads. We can display this information in table form. So we have the individual x values. X can take on a value of 0, 1, 2, or 3. And then the probability. So there were 8 possible outcomes, 1 of which generated no heads. 3 outcomes generated 1 heads, 3 generated 2 heads, and 1 generated 3 heads. So you could see that we have the probabilities here. In this case, we're listing them as fractions. And then we could also take that information and create a histogram I'll create a histogram distribution, if you will, of the possible outcomes. And in this case, the value of the random variable x are integers. So with our histogram, notice that we've centered each of those vertical bars of our histogram right on the integer values 0, 1, 2, or 3. All right, so we might ask a certain question. Find the probability that x, again, x being the random variable that represents the number of heads when we toss a fair coin 3 times. We could say find the probability that x is greater than or equal to 1. And so that means X could be 1, 2, or 3. So we would simply take those probabilities, it could be the probability that X is 1, that it's 2, or it's 3, and we're going to add those up. And so we might want you to be able to interpret this. So this is the probability that X is greater than or equal to 1, but we really want to, if we want to interpret it in context, we'd say find the probability that we would get 1 or more heads when tossing a coin 3 times, and that probability is 7/8. All right, so a random variable takes on lots of numerical values. And so just like a variable in any math class you've ever had, so we had variables that can take on lots of different values, but these values are all kind of the outcomes of some chance process or random process. So we're calling that a random variable. It's really just a variable. In this case, it's a discrete random variable because there are individual values, 0, 1, 2, and 3. Not a continuous random variable. All right. And then the probability distribution of the random variable gives us the possible values and their probability. So if we look at the table up above, we have the x sub I, which is the individual values of the random variable x, 0, 1, 2, or 3, and then their related probabilities. All right, so let's talk more about this discrete versus continuous random variables. So there's two types, discrete and continuous. The example we just saw was discrete because you couldn't have as an outcome for the x value anything but very specific values. So in this case, it was integers. But we could list all the possible values. So if we can list all the possible outcomes for the random variable, then this will be discrete. All right, so sometimes it helps to think that a discrete is going to come about by counting things, whereas a continuous is going to come about from measuring things. So if we look at the example, shoe size. Shoe size is discrete. In other words, you can't have a shoe size of 6.001, but you could have a foot length of 6.001. So the foot lengths, shoe sizes, we could list all the possible shoe sizes, right? You might occasionally get someone with a really big foot, but we could list them all. They're not an infinite set of possible values. So because we can list all the possible shoe sizes, those would be considered those values would be considered discrete random variable. Foot length, though, I could not list all the possible foot lengths. Now, I mean, if I have 30 kids in class, I might be able to list the 30 foot lengths of the kids in class, but I would not be able to list all the possible foot lengths of people I might come across. Whereas I could list all the possible shoe sizes of all the people I might come across. All right, so foot length is going to be considered a continuous random variable, and shoe size would be considered a discrete random variable. Okay, so let's concentrate for a moment on discrete random variables. And so, again, we use the capital X as the generalized idea of the value, the random variable of interest, and then the lowercase, usually with a subscript 1, 2, to indicate the individual values that the random variable capital X might take on. And then underneath that, we say P sub 1, that would be the probability of the first possible outcome of X, and then P sub 2 and P sub 3. So we have sort of in table form, the first row are all the possible values of the random variable, and then the bottom row is all of the corresponding probabilities. And we know this is a discrete because we would not be able to list all the possible values of the continuous random variable. Okay, so a couple of requirements here for the probabilities. For every p sub I, that means, it means p sub 1, p sub 2, p sub 3. In general, we'll call that p sub I. They have to be between 0 and 1. And in this case, it would really be exclusive of 0 or 1, because if p sub 1, for example, in this little table here, if p sub 1 was 0, then that means x sub 1 would not be a possible value, and then as a result we wouldn't have it in the table, right? So none of those probabilities could be 0, and then likewise none of them could be 1, because all of them have to sum up to 1. So if p sub 3 was 1, that really means the only possible value of the random variable x would be x sub 3. All the other probabilities, p sub 1, p sub 2, all of them would be 0 if p sub 3 was 1. Okay, so we say every probability listed there underneath their corresponding x values would be between 0 and 1, but exclusive. It couldn't be 0 or 1. The sum of all those probabilities, p sub 1 plus p sub 2 plus p sub 3, as many as there are, would all have to sum up to 1. All right, and then finding the probability of a particular event simply means adding up the probabilities that correspond to all the x values that make up that event. Okay. Let's look at an example. This is an American roulette table. And if you kind of look at it, you notice that there are numbers 1 through 36. Some of them are red, some of them are black. We also have, at the very left corner of it here, we have 0 and 00. So there's actually 38 different numbers on a roulette table and on a related roulette wheel. All right, so one type of bet in roulette is called a corner bet. So generally, there's lots of ways we can bet on a roulette table, and we're actually going to play. We'll play roulette one day before winter break. When we have a short day or something, we'll probably play this in class. But one type of bet is a corner bet. And that corner bet means I'm putting it on the corner of 4 numbers, so that if any of those numbers show up, I actually win some money. So let's assume for a minute that this chip that we just threw down on the roulette table is a $1 bet. And so if that's the case, then if 25, 26, 28, or 29 showed up on the roulette wheel, then I would get my chip back plus another $8. So that means I'm now $8 richer than I was before. And so my gain will be $8. If one of those numbers does not come up, say if 15 showed up, then I would lose that bet, and then my gain, or how much money I would win, would be negative $1. So if we want to look at this in the way of gains and probabilities, so if numbers 25, 26, 28, or 29 did not come up, then my gain would be negative $1. I would have lost that $1 bet. And if we think about it, what's the probability that I lose that? Well, remember that there's 36 numbers on the board, but there's also 0 and 00. So the other possibility is that one of those numbers does come up, and that means I would gain $8. Now I get my chip back, plus I get 8 more. So I mean, I really am I'm taking off the table $9, but it cost me $1 to do that. So really the gain is $8. And so now let's think about what the probabilities are here. The probability that I lose, that's the more likely thing to happen. There's 38 numbers for which I would win, so that means there's 34 outcomes that would mean I would lose. So the probability that I lose $1 is 34 out of 38. And the probability that I win, well, there's 4 possible outcomes out of the 38. So 4/38 is the probability that I win. All right, so now let's think about if I played this game many times. All right, so if I did it many times, what would be the long-term result? Like how much would I win? So let's concentrate on just like, instead of just many, let's say I played this game 38 times and I kept like that same bet on 38 times. What would I sort of expect? So you can see that I would expect if I paid 38 times, I would expect on average about 4 wins. So 4 times I would gain $8. And then 34 times I would expect to lose $1. And so we could sort of write it like this, right? Instead of writing -1 34 times, I could say 34 times -1 plus, and then 4 8, so 4 times 8, well, all over 38. But I could use a little algebra to rewrite that in another way that might look. So this is kind of like, what's going to happen long term, or what is my expected gain if I keep playing this again and again? So we could use a little algebra to manipulate that last formula, and it looks like what? These numbers should look familiar. It's the gain, right? So -1 times its probability, 34/38, plus the other outcome that's possible, 8, times its probability. So that is the expected gain. So if I, actually picked up a calculator and calculated this, my expected gain, and if I played this again and again and again, would be on average, I would lose 5 cents every time I played a $1 bet. Now, I could never lose 5 cents. Like the gain, that's not an option, right? Losing 5 cents is not one of my options for the actual outcome for any one particular game. But the average over lots and lots of games would be that I would lose 5 cents. So you might ask yourself, well, who in the heck would play this game, right? And if I'm going to lose 5 cents every time I play, why would I play it? Well, that 5 cents loss every game is a long-term occurrence, right? So that is probability, which is a long-term event. Short term, I might win a couple times and I might be up and I might actually be winning money. This is why casinos pretty much never lose money in the long term. And casinos are there for the long term. I might, as a bettor, sit down at the table, put a couple chips down, win, and walk away. But if I sat at that table long enough, then I would eventually lose the money. Okay, so we kind of saw that introduction of that expected value. So the expected value, or the mean of a discrete random variable. All right, so the mean of a discrete random variable is the average of the possible outcomes with each outcome weighted by its probability. So it's like a weighted average. And you can see here, again, we have our random variable distribution here. We have the possible x values, underneath them the corresponding p values. So the expected mean would be simply taking each x value, multiplying it by each of its probabilities, and adding them all up. And we kind of saw this when we were just talking about the last example with the roulette wheel. All right, so it shouldn't be surprising that that was the gain times each of the probabilities. Here, it's the x value times all of its probabilities. All right, an example that we use in the book is a baby's APGAR score. And so this was developed by a Dr. Apgard. She looked at a scale of 5 different criteria for newborn babies, their reaction to stimuli, all these different things. So 5 different things. And for each of the categories, she came up with a score of 0, 1, or 2. So the maximum score would be a 10. If a newborn baby got a 2 for each of the 5 categories, and then a 0 if you got none, you got no points in any of the categories. That would mean you were a pretty sickly baby. And so then you can see here, this is a probability distribution for that random variable x, the APGARD score of a randomly selected newborn baby. So you can see that, and we can look at this and say that about 43.7% of the APGARD of the newborn babies have an APGARD score of 9, for example. Okay. All right, so I created a histogram of this just in my calculator. And so you might want to do that yourself. And you would simply remind you how to do this. You would simply put your X values in list 1 and your probabilities in list 2. And then ask your calculator to create a histogram using X as your X list, and now you would use your frequency as L2. Like, we haven't really used a frequency list before, but that's what this is. So instead of listing all the how many zeros there are, and running a whole list of 1,000 babies and all their scores, here instead we just list all the possible scores and then the frequency or probabilities that those happen. Okay. You would probably, if you did this, you might have to adjust your screen to get your histogram to look kind of like this, so that each class width in your histogram is the same as the numbers, but you'd have to make some window adjustments perhaps. All right, so what would be the probability if we randomly select a baby, a newborn baby, what would be the probability that the APGARD score for that baby would be greater than 8? So like we were talking about before, the probability of an event is simply adding up the probabilities for all the X values that satisfy that event. So in this case, greater than 8, that means we would add up the probabilities for 9 and 10. And so that's about 49%. So 49% of babies have a APGARD score of greater than 8. All right. What if we asked what's the probability that an APGARD score is greater than or equal to 8? All right, so this is very similar, except now we would want to include the 31.9% for the 8. So now we're adding up the 3 highest probabilities this time. And so that would be an 80, almost an 81, 80.9% of the babies newborn babies have APGARD scores that are greater than or equal to 8. So 8, 9, or 10. Okay, so let's calculate the mean or expected value of the APGARD score. So that means if we were to look at many babies, what would be the average APGARD score for those babies that we were looking at? So if we took a sample, for example, of a bunch of babies, what would be the average score or the mean score or the expected value? All right, so we see, making sure that we understand the distribution, the probability distribution that we have. So we see that 1 out of 1,000 babies has an APGARD score of 0. So 1/1,000th of the it's probability that if we randomly selected a baby, the probability that they would have a score of 0 would be 1 out of 1,000. And so 6 out of every 1,000 babies would have an APGARD score of 1. You can see that if we look up here in the table. All right, so how would we calculate the expected value? Well, we simply take each value and multiply it by its probability. So we're going to take 0 and multiply it by 1,000th, and then 1 times 6,000th. 2 times 7 thousandths, and so on. We do that and do that for all 11 values, 0 through 10. And then we would simply add all those up, and we get something like 8.128. And so what does that mean? The mean APGAR score of randomly selected newborn baby is 8.128. This is the average score. If we looked at many, 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 many babies, that would be the average score that we would expect to see. Okay, so we want to talk about how to calculate the standard deviation or the variance of the discrete random variable. And so in that case, again, we have a bunch of x values for the random variable and a bunch of p values, all the probabilities. And in this case, and again, we're not going to be doing this by hand very often, especially if we have something like 11 possible outcomes for x. It gets pretty tedious. But we take the x value and subtract the expected value. That's that 8.128 we just calculated if we're talking about the APGAR scores. So the difference or deviation for the particular x value from the mean squared times that corresponding probability for that x value. We do that, add them all up, and that would be the variance, okay? And so the standard deviation, we would just simply take the square root of that value, and that would give us the standard deviation. All right, but again, we're not gonna have to do that very often, especially if we have a lot of different x values. All right, but how would we do it here? Again, we're going to take each x value, subtract from it the mean, the expected value, square that difference, multiply it by its probabilities. And then you can see this would be a pretty tedious process to do. And in this case, the variance is 2.066. And we take the square root of that, and we get the standard deviation of the random variable x to be 1.437. And so then how would we interpret that? So a randomly selected baby's APGAR score would differ from the mean, with typically the mean being 8.128. So the typical baby's APGAR score would differ from that mean score by about 1.4 units. And that's how we interpret, how we interpret all standard deviations, right? It's the typical deviation from the mean, in this case, the mean or expected value. All right, so this example is the random variable x, the number of televisions in a random sample of 100 US households. And they're asking us to find the mean and the standard deviation. So let's show you how you would find these using your calculator, because we're really not going to expect that you're doing this by hand. This one's not too bad. There's only 5 possible outcomes, 0, 1, 2, 3, or 4 televisions, and their related probabilities. But still, we're going to want to be able to do this with our calculators. So the first thing we do is we put the x values in list 1 and the related probabilities in list 2. All right, once you've done that, we hit the edit and then the stat and then the calculate, and we want to do a 1 var stat. And then if you have the newer operating system in the TI-84s, you get a very user-friendly list here. We want the list to be list 1, and we haven't really done this much, but now we have a frequency list. And that frequency list, we want to say L2, and then we'll just hit calculate. Now, if you are using the older operating system or an older TI-83, then what you'll do is when you hit the stat, calculate, and 1 var stat, it'll paste this command back onto your home screen with the cursor blinking next to it there. and then you will type L1 comma L2. So second 1 comma second 2. All right, so regardless of which way you do it, you'll eventually get this this printout here. Now you might have to scroll down to see some of the other things, but the key issues that we're looking for is this thing here, which is our X bar, and this thing here, which is our standard deviation. Okay, so much quicker, much easier than trying to do all that by hand. Still important for you to understand how to do it by hand, but you know, you'll have formula sheets that would have those on there anyway. I think our formula sheet has this on there. Okay, so we want to be able to do it just on our calculators. All right, so now let's start our discussion of continuous random variables. So we're gonna, most of what we do here on out, and most of the rest of the book is going to be dealing with continuous random variables. So they are rather important. All right, so continuous random variable means that we wouldn't be able to list all the possible outcomes for a particular variable if it's continuous. And so we've already looked at this as like a density curve. We looked at how density curves, you know, the probability of something happening is going to be related to the area under a density curve. All right, so we're not going to be able to list all the possible outcomes of X, like foot lengths, right? We can't list, there are so many different possible foot lengths that we can't list them all. All right, so here we have an example of a density curve. Remember that the area under the density curve is 1. So if I ask what's the probability that I'm going to randomly pick an X value and that that X value would be greater than or equal to 2 and at the same time less than or equal to 4. And we could look at this area, and this area is going to correspond to that. The area under the whole thing is 1, so that looks like it would be 1/2. Now, what's the probability that I would randomly pick an X value of 2? And so just like we saw with density curves before, the probability of a particular value is always going to be 0 because there's no area associated with that. All right, so the vertical line right above 2, lines don't have any thickness. And so when we do continuous random variables, we cannot calculate the probability of a particular value, only a range of values. All right, what if I ask this question? What's the probability that X is between 2 and 4? So that would be exclusive. Well, you could probably guess that that's going to be the same as the probability that X is greater than or equal to 2 and less than or equal to 4. So inclusive, exclusive of those boundaries 2 and 4, it doesn't matter, because if we add a 4 and a 2 to that area, it still is going to be the same 1/2. So it doesn't matter for continuous random variables whether we include the and equals to or just the less than sign. All right, so a couple of things we need to know about. The probability model of a discrete random variable. When we're dealing with discrete random variables, X assigns a probability between 0 and 1 for each value of X. And so for a continuous, and now we're just going to call it Y to differentiate it from the X, which was the variable we were using for continuous, for discrete. So now we'll go to continuous, and we're using the Y just to differentiate them here. No real importance. We don't have to use Y for continuous and X for discrete. But we're just kind of differentiating them here because now we're switching over to continuous, so we're going to use a Y. Okay, so the continuous random variable Y has infinitely many possible values. I could not list them all. There's an infinite list. Okay, all continuous probability models have a probability of 0 at any individual value. So we saw this in the last density curve in the last slide. probability that I would have an x value of 2, or in this case a y value of 2, will be 0. It has to be intervals of values that they're the only ones that have positive probabilities. All the other ones are going to be 0 for individual values. All right, so let's look at an example. The heights of young women closely follow a normal distribution with a mean of 64 inches and a standard deviation of 2.7 inches. Now, choose one young woman at random. Call her height Y, capital Y. If we repeat the random choice many, many times, the distribution of values of Y is the same normal distribution that describes the heights of all young women. So, what is the probability that the chosen woman has a height between 68 and 70 inches? All right, so we can look at this as a normal curve, as a density curve, and we can do some shading. And so what we're going to do here is look at this as a 3-step problem. So for this chapter, when we're dealing with calculating probabilities, we're going to want to look at a 3-step problem. All right, so we're going to use 3 steps when we calculate these normal probability calculations, or when we try to calculate a probability. And the first step is going to be three things required in the first step. So first, we want to define a random variable. So in this case, the height Y of a randomly chosen young woman. So that's going to be the Y is going to represent the height of that randomly chosen woman. And then we're going to say that the distribution of all the heights of all the women are normally distributed with a mean of 64 and a standard deviation of 2.7. And then thirdly, in the first step, we want to state what probability we're actually calculating. So we want to calculate the probability that the randomly chosen woman is between 68 and 70 inches tall. And we can say that in symbolic terms, like I have here listed, or we could write that out in words, but I think it's a little bit nicer to write it out symbolically. Okay, the part 2 is going to be to show the calculations and also to draw a normal curve. I'm going to require that whenever you are dealing with a normal curve calculation, that you draw the normal curve with a shaded region. All right, so we can see here we've indicated on the normal curve 68 and 70, and we've shaded it in between. And we know that those, of course, are above the mean of 64. So we're going to do that shaded region on the right side of our normal curve. We can calculate our z-scores for each of those. The 68 corresponds to a 1.48 z-score, and the 70 corresponds to a 2.22 z-score. We would go then to our z-score table and calculate or find what the area to the left of both those z-scores are. We would subtract them, and we would get something close to 6%. All right, we have another way of doing this now that we haven't done in the past, so we don't have to use the normal z-score table. What we can do is we can use our calculators. Okay, so we would pick up our calculators and we hit the second and then vars button. That the second function of the vars button is distribution. So we hit second distribution, and we go down to normal CDF, and we click on that. And then what we see next depends on if we have the older or newer calculators. The newer calculators give us sort of a user-friendly interface screen where they ask for the lower value, the upper value, the mu, the mean, and sigma, the standard deviation. If you have the older TI-83 or the older operating system of 84, then you would get normal CDF and then a parenthesis paste it back on your home screen, at which point you type 68, 70, 64, 2.7. And then you plug that in and you'll get the same answer. Now, when you write that out on paper, right, because you have to show me work to get full credit. And so you have to write that out, but you can't just write 68, 70, 64, 2.7. You have to say what those things are. So the lower bound, the upper bound, the mean, and the standard deviation. All right, and indeed, when you are doing a problem on the AP exam as well as on my tests, you should be making sure that you draw a normal curve with shading. Right? You will lose points if you do not have a normal curve with shading for a problem similar to this. All right, and then it's not just enough to write out the equation. What you want to do is on the bottom here, so you do normal CDF, make sure you're including the lower, the upper, the mu, and the sigma. Now, you're not actually entering those into your calculator. In the calculator, you're just doing the 68, 70, 64, and 2.7. But when you write out your work on your paper, you want to indicate what those four values are as opposed to just writing them down, okay? And then, of course, again, shaded normal curve with labeling. All right, so you notice we got very similar answers. The z-score calculations are only accurate to a certain decimal places, so you'll see probably that we won't get the exact same answer. The calculator answer will probably be a little bit more accurate. Okay, so finally, the third step is answering the question, right? So that would be, your conclusion. So in a sentence, answer the question. So what is the probability that we randomly choose a woman and she's between 68 and 70 inches? So we want to say that there is a 5.6% chance, or that the probability is 5.6% that you would that a randomly chosen young woman would be between 68 and 70 inches tall. Okay, so your homework tonight for next class are these at the bottom, and now the 23 and the 26 are 3-step problems. So make sure that you look back at the last example to get a model of what that should look like. So the step 1, you want to define the random variable. You want to say what the distribution is, and then and this is mostly for continuous random variables, I think. I'm not sure we'd use this process for a discrete random variable. And then we also want to say what it is that the probability was trying to calculate. So that's step 1, to find the random variable, say what the distribution is, and then what the probability we're trying to calculate. And then part 2 would be to do the calculations, normal curve included. If you're using your calculator, fine, but make sure you're saying what the different parameters are that you're putting into your function, into your calculator. And then finally, in a sentence, answer the question.